So before we get started, I have a question for everyone, which is that, there's like a music, this music. Have you heard this somewhere? Where? Have you ever listened to this music? Is it familiar? It seems yes. Yes. Do you know where, or just it's familiar but you don't know where? It's familiar. No, nobody, no? Okay, it will become clear in a second, okay? Because I was choosing to do something a little bit experimental today, so let's see how it goes, okay? Okay, so I think we are ready to get started, and it will become clear just now. Ladies and gentlemen, welcome to this Aldan Airlines presentation. Before we get started, I'd love to guide you through some of the features of the presentation itself. We will have 8 sections, 2 at the start, 4 in the middle, and 2 at the end. We also have some pink boxes at the end of each section, which are important messages to remember. So those are things that we will go back to when we finish the presentation to build a nice summary of what we learned today. Also, I will choose to be more accessible, so easily understood rather than precise. But if you want the precision, you will also have the bibliography. So you will have the references. I'll give that to you at the end. So you just need to take a note of the small thing that's down here, and you will be able to check it later, okay? Another thing is that the presentation is in English, but I'm super happy to take questions at the end in, a bunch of different languages, Spanish, Portuguese as well. I'd be super happy if I get some questions in Portuguese. So feel free to ask in any language, basically. Having said that, thanks a lot everyone for being here, and I really hope you enjoy this Aldan Airlines presentation. Okay, that was the experimental part. We will be going on a trip, on this knowledge graph world. But first, we need to understand what's a knowledge graph, right? What's a knowledge graph? What's this thing? How many of you have heard about it, or have some familiarity with the concept? There was a talk just now about this thing, so I hope so. One person. So a few hands, okay. It's a very simple thing. A knowledge graph is just a type of data structure. It's a type of NoSQL data structure where what I have are circles, and they are connected with these lines. You see, I have a circle and a line. That just means that concepts are connected. So for example, I will have, if you think of Facebook, right? If you think of Facebook, you have somebody who's connected to this person, but maybe this person is not connected to this one. If I have a line, they are connected, otherwise no. Very simple, right? That's the data structure itself. We use that to represent all sorts of information, so it can literally be anything. That's the strength. It's a very simple data structure, but you can put anything here. And that makes it very solid, but on top of that, we can also apply classical artificial intelligence on top of this thing. So that's very interesting. But what we can also do is, because language models are very trendy and everybody is talking about them, we can also put that thing in knowledge graphs. We'll see how a little bit later. The good thing is that we can combine the 2 approaches. That's what we are going to talk about today. So I hope that's clear. This is a simple knowledge graph, just a type of data structure. It doesn't have intelligence by itself, but it's a very solid structure because we can use it to represent basically anything. So that's a knowledge graph. But how can we apply AI to this thing? What are the algorithms that we can use? Well, I'll give you a basic idea. So first of all, there's a shit ton of different algorithms that you could use. This is a field that's evolving all the time. So I'll just give you a simple idea, and all of the rest of the algorithms are just like small changes on the basic idea. For those of you who just want like the general thing, you just need to listen to the first minute, and then I'll give you more details on how they work. Okay, so I'll try to be like catering to people who want to know more and people who want to know a little bit less. So what's the general idea of how we train artificial intelligence on a knowledge graph? Well, I have a knowledge graph here. You can see that I have like one gene, some diseases. Here I'm saying gene 1 causes lung cancer. Gene 1 causes heart disease. Gene 2 causes lung cancer, etc. Right? But I'm also saying gene 2 doesn't cause heart disease, etc., etc. So what I do is I take the knowledge graph, I give it to the machine, the algorithm. It does some magic. We'll see how in a second. And then I get a result, which are embeddings. If you are familiar with language models, you will have heard of this thing. What's an embedding? An embedding is a concept. So we will get representations of what it means to be gene 3, or what it means to be lung cancer. We will get numbers representing each thing, and then we can use some metrics to extract conclusions. Now, we'll dive a little bit deeper, but that's the general idea, okay? So, deep dive on this thing. How does it work? Well, this is the graph that we had before. I'm gonna do one thing, which is that I'm gonna have code here for the people who like code, and I'm going to have a visual representation here for the people who like visualization. So I'll have the two things at the same time. But I think it's going to become clear in a second how it really works. So first of all, what we need to do is we need to assign random numbers to each of the things in the knowledge graph. Here you see that I literally put the different things in random places, right? Just initialize randomly, put them in some place. Okay, very good. We initialized the embeddings. Now, what we do is that we will start training the thing. Now, let me make a first comment before I continue, which is that we don't only have just positions for the nodes in the graph, we also have an embedding for the relation. You'll see why this is important in a second, but you see that we have some numbers here as well, right? Very good. So, how do we train this thing? Well, let's move forward a little bit. Training. So what we're gonna do is that we will go through the different relations in the graph, and we will optimize them. Let me just take one example so it's clearer. Let's say, for example, gene 1 was connected to lung cancer, right? It was in the graph before, we had a line. So if we take the relation causes, you see that if I do 210 plus 5 minus 1, it takes me here. That's my prediction. So what I'm doing here is I'm telling you, if I go from gene 1 to the thing that I think should be the thing that this gene causes, I'm going to land here. So if there was a disease here, that's my prediction. Now, I know that gene 1 is connected to lung cancer, right? So what I would want is that this doesn't take me here, this should take me here. So I adjust, I optimize the thing. I say, how wrong am I, right? Like, I'm a little bit wrong, I calculate that, this is how I could do it, for example, and then I need to change my embeddings so that they align with what I would expect. So I make a simple adjustment. I'll give you a simple idea. This is not exactly how it works, but for example, you could say, I take the difference and I make it half, and I apply that difference here and here. So I optimize, it moves here, and now I have a perfect prediction. Simple, right? It works. Very good. Now, if we do this thing many times, we should land with a representation that could look, for example, like this. Here you can see that gene 1 was related with lung cancer and heart disease at the same time. So the embedding landed somewhere in between, right? It's both telling me one thing and the other. But for example, I guess that in the graph, gene 2 was only connected to lung cancer. So the optimal position is here. That's clear, right? Very good. So now I can do inference. And what I can do specifically is that I can measure the distance between my prediction and the real thing. So for example, I know that gene 4 is connected to heart disease. So I have a small distance here. But I also know that gene 2 is not connected to depression. So I have a bigger distance. And if I do this thing, I can start doing interesting tables that can be very helpful in real life. So for example, if I ask you, if I'm a researcher and I want to create a new drug, this is a real example, we work with these things. We get questions like, what genes are most related to this disease? We take all of the different genes in the human body, the proteins they encode, the organs that they are expressing, the different variations of the genes and how they are connected and what drugs target the different genes. You put a lot of information in your graph. You train your embeddings using the same technique. And then you build a table like this one. You just start measuring the distances. So what you get is, oh, this gene is very close to lung cancer. So probably if you want to start doing research, you should start with this gene. You shouldn't start with this one. You know, pick the top predictions. This is an important step forward because when you try to do research, up till, well, some years ago, it was just happy ideas that people were having. You know, I'm a researcher, I see a paper that I think is interesting, so I'm gonna do research on this gene. But that failed a lot of times. When I say a lot, I mean 80% of the times it failed. That's huge, right? It's a lot of money spent, a lot of time. If we start with better predictions, we can just cut that time a lot. So that's a strong application that we have. Now, this is great, right? Fantastic. Yes. My message here is that AI can put intelligence into knowledge graphs. And that's something that's very cool. So, perfect. It really seems perfect. Now, I'm going to put my airplane hat again for a second. Ladies and gentlemen, we hope you're enjoying your flight. We will now pass through the cabin with our selection of scratch cards, things that you can get with knowledge graphs. You want one, sir? Yeah, very good. So, you know, you can solve your life with the different advantages. Take one, sir. That knowledge graphs can bring to your life. Let me just get something here. Microphone. Oh, I need a microphone. And, oh, you want one? Thank you. So, oh, I heard we have a winner. Sorry, did you just win something? Oh, what can knowledge graphs bring to you?
Understanding customers better.
Understanding customers better. Oh my God, yes, a winner here. Fantastic. What about you, sir? Did you win something? Oh my God, yes, true. This thing, it's amazing for that, right? What about you, sir?
Detecting fraud.
Oh, detecting fraud, of course. That's very nice things that we can do with knowledge graphs. Fantastic, yes. This is great, it looks like the pilot has just switched on the fasten your seatbelt slide. It looks like we're going to have some turbulence in the flight. So please remain seated. Don't panic. We're having some turbulence here. Oh, shit. Oh, my God. Oh, no. Oh, we're going to crash. Okay. We crashed. So yeah, we crashed. Oh my god! Oh, horrible. Where did we land? Where's this place? It looks very bad, right? Horrible land. This is not where we were heading. We were heading to the promised land of artificial intelligence, knowledge, nice things, unicorns. But this is not a nice place. This is, I think I know what this is. It's the land of the limitations of knowledge graphs. It's a horrible place. It's a horrible place, really. Trust me, you don't want to be here. I'll explain what's the problem. Let's talk a little bit about limitations. What's the problem with this knowledge graph embedding thing? So you see, I didn't lie to you, but there's something I didn't say. We can have this graph, right? And we can start doing predictions if we train our embeddings in this way we just saw a second ago. But there's something a little bit weird. Take a look here. I'm going to make a change, okay? So 3, 2, 1. What's the change? I changed the words. And my question to you is, if I change the words, if I take a completely different graph, because it's super different, right? If I take something that's not related at all, what happens here? If I train my embeddings, am I going to get a different result? No. I'm going to get exactly the same thing, because what I'm doing is just seeing if things are connected. I'm just looking at where they are, but I'm not looking at what they are. And that's a little bit strange, right? And what happens if now instead of likes, I say the opposite thing? What happens if I say hate? I should get a different result, right? Because I'm saying the opposite. If I predict on something that's the opposite of something, I should not get the same thing. But, well, I would get the same thing. So that's strange. It doesn't make a lot of sense, right? Yeah, that's a problem. Classical AI has some limitations. It's an awful place. It's an awful place. Let me see if I maybe can get us out of here. I'm going to use the radio. Hey, help, help. We need to get out of here. We're trapped in the land of the limitations of knowledge graphs. Help, please. Oh, a stranger.
I regret to inform you that your radio is not going to work.
Oh, well, can you maybe help us? Is there something we can do here?
I will be happy to show you the way to a land where you will find the solution you are seeking.
Oh my God. Oh yes, of course, we'll follow you. So now we follow the guy. And
we have arrived.
Oh, what's this place? Yes, the land of language models.
This is the place where you will find the solution to all your problems.
Thank you, thank you. Let's talk a little bit about this thing, about LLMs, right? Just before we move on, who are you? Could you tell us a little bit more about you?
I'm ChatGPT,
of course,
a large
ChatGPT.
language model created by OpenAI.
Very good. Okay, let's talk about it. Let's talk about it. Knowledge graphs and language models. How can we merge the two things? Why would we want to merge them? We want to pay attention to the words, right? We want to be having different results or be able to take the textual information somehow into our knowledge graphs. So I'll give you different avenues in research that this thing is, let's say, getting introduced. There's 100 different papers talking about this thing, so I'll talk about 3 of them, okay? There's more. And like if you want to dive a little bit deeper, I have like some extra slides if you want at the end, so like we can talk a little bit more about that, but I'll give you 3 simple examples, and we learn about possible applications. So first, what I'll talk about is a thing that's called language model augmented knowledge graphs. That means I'm going to use a language model to make knowledge graphs better. Then what we'll talk about is knowledge graph enhanced language models. It's the other way around. So I'm gonna use a knowledge graph to improve sort of a language model, right? And then what we are gonna talk about, that's the third thing, it's a thing that we call a hybrid approach. So I'm gonna try to really merge the two things and have something that's a mixture of knowledge graphs, language models. Okay? Very good. So again, there's really a lot more things that we could talk about, but we don't have all the time in the world. So I'll give you some ideas that you can start to think about. The first of them, it's this thing that's called BERTnet. This is a paper that was published by some researchers in UCSD. And I'll give you the idea here. I'm going to put like a black box explaining each step, and then I'm going to cover the parts of the system to just get the idea of what each section does, okay? So what we do is, I'm going to take an initial prompt, and I'm going to take some examples of things that apply to that prompt. For example, the potential risk of eating candy is tooth decay. You give me a prompt, some examples of things that apply to this prompt, and then what I'm going to try to do is I'm going to create a knowledge graph out of nothing. I'm going to use a language model to extract the knowledge that it has already to create this knowledge graph automatically. Advantage here, you don't need a person. You can literally save on costs, time, etc. You just automate the whole process. So how does it work? I give you a prompt, I give you some examples, and then what I'm going to do is I'm going to take the different phrases. So I'm going to use the prompt, and I'm going to replace that thing with examples. I'm going to paraphrase the prompt. Why am I doing this? Well, you know, when I ask ChatGPT something in different ways, sometimes I get different answers, right? So this is why. I'm going to generate different ways of asking, and I'm going to extract the different prompts. So in the end, I'm going to have a set of prompts like the potential risk of A is B. A may lead to B. If you do A, you may be at risk for this other thing. I generate different ways of asking. And then what I do is I'm going to rank the ways of asking, the different prompts, to get an idea of what are the best questions that I can ask. I take the examples that I had before, and I look at what were the questions that were most likely to predict those answers. So I get a ranking here. You see? Prompt 1 is better, prompt 4 is not so good, but still good, etc. So I reweight my prompts, and then what I do is I literally start giving the model the prompts, and I generate as many things as possible. Lots of things, right? Like hair infection, alcohol suicide, food obesity, whatever the model thinks of. Now, I will have a lot of hallucinations here, but what I do after this is I filter that. So I get the different prompts with the weights that I assign to each prompt, and I will take my predictions and I will see how each prompt tells me that this thing is likely. So if my best prompt tells me it's very likely that smoking causes cancer, I will trust this thing a lot, and I will not think it's a hallucination. But if my bad prompt tells me speeding causes a crash, maybe I won't trust that thing so much, you know? I'm not saying it's wrong, but this is the way I do the algorithm. Clear? Yes, very good. So I use the best questions to extract knowledge from the LLM in an automated way. So that's the strength here. It's super simple to use, you know, like you just need to give a prompt, examples, and it does the job. That's very good. Super nice, very good. Now, I'll give you an example of the second thing. The second thing is, how can I use a knowledge graph to improve a language model? So, you know, I can ask ChatGPT for a question. For example, I don't know, like I give you a question from a test, and I ask you, what's the answer here? And maybe ChatGPT will get it right, but maybe it won't. You know, many times there's this problem of hallucinations that everyone talks about. What can we do with knowledge graphs? Well, I'll give you one system, GreaseLM. You will have the references, right? Remember, they are all here, so if you want to go check it out later, you can. The idea of GreaseLM is, I'm going to start with a question, a simple question from a test. And then I'm going to give the system some options. Here I just have one, but I will give 5 options. So if it's not used for hair, a round brush is an example of what? Art supplies, different options. Now, ChatGPT would just tell you, oh, it's this. And then you don't know why. Maybe it's hallucinated. You have no idea. This thing does something different. So what we do different here is that we will first do the same process as with ChatGPT. We will just take the question, we pass this through a language model, no changes here, we just pass it, right? Okay, but the difference comes now. We also get a small graph that represents the things that are related to this. So we were talking about art supplies, hair brushes. You see, we have the entities here. Hair brush, related to round brush, painting, art supply. We get knowledge graphs of things that are somehow related to my question. Sometimes, here this example, of course, it's a very good example of things that work. Sometimes the knowledge graph that I extract is not that good. You know, maybe there's things that are not necessarily related. But that doesn't matter so much because the system will learn to ignore that. Like the noise that I get here, I just ignore that. So what I do is I take a small knowledge graph and I put something very special. You see this? That's the key. That's the point of the whole paper, the interaction node. This thing will allow the language model to communicate with the knowledge graph. So we get this mini knowledge graph. And now what we are going to do, you see we have some text here and a separate knowledge graph. So they are not together in any way. We will merge them now. So what we do is we put this thing that's called the GreaseLM layer. And what it's doing basically is this process of enabling communication. And specifically, how this works is that I will have a special token here. I think you can see it, but it's here. In the text, I place a special token at the start, like a special element that enables me to communicate this embedding, I have it here, with the special interaction embedding that is in the graph. So I take the 2 embeddings, I put them together, embedding 1, embedding 2. I pass them through a multi-layer neural network, and then I separate them again. So it's like this. Then I do that, and after some different layers here of repeating the same process, you know, communicating like this, I will get an embedding here and an embedding here that I can actually use to infer in a classifier what's the correct prediction. That's how it works. Very smart, right? That's the whole architecture of the system. I know it's a little bit complex, but I think this way, you know, seeing it step by step, it just becomes a little bit clearer. If you have questions, I'd be happy to answer now before we move on to the next system, because I know sometimes it can be a little bit technical. So, any questions? Yep. Yep.
Geralmente, quando a gente lida com o LLM, geralmente as relações entre os nós, geralmente ela é meio rasa, ela não vai tão fundo nessas relações, tem um limite. A experiência que você tem nesse nível, você consegue realmente chegar a vários níveis de...
So you mean like the representation capability of the LLM, like the abstraction capability is not very good, And like the answers that,
It's a challenge. So if you ask like, okay, land is related to, I don't know, strawberry, but you cannot go for land to, I don't know, airplanes, because it's shallow in the sense that it's not going deeper in the ontology and the semantics for it, and we can create all the relationships, all the ontologies.
oh yeah,
The graph database, not graph, knowledge graph.
yeah. So let me repeat your question just to make sure I got it right, because I think it's interesting for everyone. Here you are, the microphone. Yes. So I'll repeat what I understood was your question, and if it wasn't this thing, you can ask again. What I understood is we have this knowledge graph here, but what happens if we miss information? We are not able to answer the question if there's missing links, things that we can't look at, right? That's a limitation. I mean, that's a limitation of the paper. You would need to look into possible improvements of the system. You know, it's not perfect. What they do to try to address that is they take the bigger neighborhood. It's like they take up to 3 hops for each thing. You know, so if I have this thing, they go very wide. It's not here because it's just an example, but they really go very wide. So they try to include a lot of relations and ways to communicate that way. But it's true that if you're missing things, that's a limitation. There's other papers that address that. But yeah, that's a limitation. Other question before I move on to the next system, maybe? Yeah. Yeah, sorry. The microphone. Yeah, I forgot.
How do you combine these two? Let's say they are both embeddings, but they come from different places. Is there a special way of combining? So when it's typical RAG, everything is text. You just join them like sequentially. But here, how does it work?
This is the super interesting part of the paper. This, like literally, this is the whole contribution. What I do is, like at the start, I don't know if some of you know models like BERT. BERT has a special token at the start that represents the text. We are doing something like that here. So here we will have our text, and inside that text, there's a special token, like a word that is the key point to communicating with the knowledge graph. I will take only that word, and I will just pass it through a model, smaller model, a neural network. And what I do is I put the embedding of the word and the embedding of the graph together. Literally, you know, just imagine my embedding here is 1, 2, 3, 4, and this is 5, 5, 6, 7. So I do 1, 2, 3, 4, 5, 6, 7, and then the neural network, you know, it can mix the different things. So here, I get a mixed representation, and well, I covered that part here, but what you can see here is that because I'm mixing the things, the language model then can pay attention to that special token, so the information keeps flowing. And in the end, what I get is that the represented version of the text, it's mixed. You see, it has like this gradient here that represents this idea of mixing. That's the whole thing. I hope that's clear.
Okay. And the red part actually takes a bit of the entire knowledge graph, or it only represents?
Yes. So the information, that's true, very good point. The information also flows here. This is a GNN, so a graph neural network. I don't have time to explain this, but you will have information flowing. So the different nodes also communicate with each other, so you will have information going from here to here, and then this goes to the language model. Yes.
Thank you.
Very good. If you have other questions, I'll take them at the end, okay? And I'll move on to the third example. The third example of a paper that is very interesting, because this thing is only for question answering, right? Like, you are only training a classifier that gives you, it's this. But what you can do is that you can merge the two things. So I'm going to go for something really hybrid. This is called CS-prom KG. How does it work? Well, first, I will have my different embeddings. You remember when we were looking at the example before, we had like numbers for each of the things. This is the same. I have embeddings for all of the things in my knowledge graph. So that's not changed. But now what I do is I'm going to take the embeddings, so first embedding, second embedding, and I'm going to also put the text of the things. So for the embedding of Steve Jobs, now here I'm going to write Steve Jobs, the words. Separator, place of birth, the words again. Separator, the thing that I get to, so the object. You know, Steve Jobs was born in... No, that's wrong, sorry. That's place of birth, that's the date. That doesn't make sense. That's a great question. I have to... Did they do something wrong in the paper here? I'd have to check. Because the idea here is that you give the text of the first thing, the text of the second thing, and the textual description of the thing that I get to. So it should not be that. It should be the text of San Bernardino. I think he was born in San Bernardino, right? Yes. So what I do is I pass my embeddings through a language model. Literally just pass the embeddings here. Now, the interesting thing is that because I'm putting my embeddings here, and I also have the textual embeddings here, I will make them interact with the text. So you see that there's an attention mechanism that allows information to flow here. It mixes the different representations. So this way, I don't just have my embedding that doesn't know about the text. Now it's able to look at the text that I have here, and it's able to, ideally, change the representation using the textual information. So it's able to somehow learn from the text, right? I do this thing many times. I pass my text through the different layers of the language model, and then I get my embeddings here. That's the result. Now, what I do with that is that I'm going to take the results of the interaction, and I'm going to repeat the theme from before, you know, from the first part of the presentation. I'm going to train just a very simple algorithm like the one we were seeing, using a classical scoring function. So I'm going to try to reduce the distances between the embeddings. What I do here, the key difference, is that now I looked at the text. If you remember, the whole problem here was that if I go and I change the words in the knowledge graph, I'm going to get something different, right? Here it's different, because now I'm actually looking at the words. So those words will influence the embeddings. And when I influence my embeddings, if now I go and I say, instead of likes, it's hates, then I'm going to have something completely different. The result is going to change. So the strength here is, you can do anything you want with embeddings. I can make these tables of gene disease associations or things like that. You're free to do whatever you want, because the embeddings that you have here now, they have seen the text. So they know the textual information. That's the strength. I hope that's clear. And if you have any questions, now I can take them before we really move on to the conclusion and we close nicely. So, any questions about this one? If it's clear, I'm very happy. I think it's like a simple idea, right? But the key idea is I'm going to take the different things, put the text here, and then get a hybrid embedding, sort of. So, very nice. Let's conclude here. I'd say in general, the idea of this section, language models, knowledge graph, is that we have thousands of possibilities. I just talked about 3 papers, right? But there's like a lot of them. And I'd say that in general, the things that are lacking here are how reliable are you actually, like how much do you protect my answers from hallucinations? That's something that many papers don't actually answer 100%. Another thing is when you mix the embeddings, some papers just fail to get the whole point of really taking the information of where things are placed and the text what they mean. Like many papers just pay more attention to one of the things. That's why I like the third one. You know, the third one is like giving equal weights to the things. There's a lot of research, and if you want to look into that, you can message me on LinkedIn and I can send you some papers. We'll have the references for these ones and some extra ones. But that's a message. A lot of things to do, a lot of work. So having said that, let's recap. Ladies and gentlemen, thanks a lot for flying with us today. We learned some very interesting things. First of all, we saw that knowledge graphs can literally be used for anything, right? You can put all sorts of information into these data structures, very solid. Now, you can use AI, classical AI, they can put intelligence into knowledge graphs, but it's also true that we have some limitations, some things that it's just not so good for, right? So what can we do here? We can mix that with language models, and when we do that, we have a world of possibilities here. So, well, we hope you enjoyed your flight today with us. Just one last ask from my side, which is that if you can scan this QR code, this is feedback, but it's also the bibliography. So if you want to get the bibliography, it's at the end of the feedback form. It's, you know, when you like open like a New York Times website and it tells you you have to pay before you read the thing, this is the same thing. So, feedback form and bibliography and also my LinkedIn, I think it's here, everything, you have it here. So, thanks a lot, really. It's really been great to experiment a little bit with you today, and I hope to see you at another Aldan Airlines presentation. And we have 5 minutes at the end if you have any questions in general, not about those specific systems, but about the evolution of the field or whatever you would like to. The microphone, sorry. Oh, yeah, very good.
I would like to know about practical implementations of these techniques. Maybe there are some existing tools that we can use and leverage in our solutions.
Very good question. So, I mean, that's really a very good question. So the systems I put here, I put them because there's open implementations in GitHub. So I used to do this talk with another system that's called CS-Prom KG, which no, sorry, that's the last one, right? Or LLM, it's another system. I didn't put it here because they didn't publish the source code, and I was trying to replicate that, you know, and like sometimes in research, you can just publish research without giving people the details of what you actually implemented. I tried to only put things here that you can replicate. So if you go to the repo, let me see if I can open that. Well, it's going to be a little bit complicated, but in the bibliography, you have the paper, and they literally, it's in the first page. You can go here, Stanford, NLP, blah, 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 and that's the code. And you can literally replicate the results. I was running the system, and it works. So it's going to work for CS-Prom KG, the last system. Also, the second one, they have replicable results. And the first one, it's also published. So those ones, you can go and try them. However, it's true that maybe they are not so user-friendly. That's something that researchers, I'd say, are not very good at. You know, making libraries or usable things. It's more like you can run the experiments, and that would need some adaptation if you can actually, if you want to put that into like a production-ready thing. Having said that, it's very possible to do it. You know, like the code is here. It's just, it needs some tweaking. So you're more than free to look at the code. You know, it's just like some PyTorch lines. It's not so complicated, but at least I tried to put something that was replicable, and I tried to take out these things that didn't have source code or, you know, didn't enable you to replicate them. So I hope that answers the question. Yep. Any more? Very good. So thanks a lot. Thanks a lot for coming. And if you want to ask anything, like I'm around here, you know, coffee break, whatever. So very happy to having talked with you for these minutes, and have a great rest of the day. Thank you.